Welcome back. Today we're going to talk about Cauchy sequences and their relationship to convergent sequences. So let's remember what a convergent sequence is. A sequence AN converges to L if this is true. For every epsilon, there exists cap n. For every n, if it is beyond cap n, then AN minus L is less than epsilon. What does that mean? That means effectively that the sequence is getting closer and closer to L. The distance from L is this distance epsilon here, and the sequence is getting closer and closer to L. That is, if you're willing to read far enough down the sequence, and how far down you have to read is this cap n here. So there is a position cap n, and then beyond that distance, all of the distances between the sequence terms an and the limit L become less than epsilon. So let's contrast this against the new definition of a Cauchy sequence. We say a sequence an is Cauchy if, and we have something very similar here, except instead of one n here, we have two different positions in the sequence. And notice that there is no L. So the first thing, before we even read the logical structure of it, there is no L in this, but there are two different things here, m and n, which are positions, and both of them are assumed to be beyond cap n. So for every epsilon, there exists a cap n, such that for any two integers, if they are beyond cap n, then here, where we would have an minus L is less than epsilon, we have an minus am is less than epsilon. And so what is this really saying? This is saying that provided you are willing to read far enough down the sequence, then the terms are not close to L, they are close to each other. And this distance from each other is controlled by epsilon. So if you want to get all of the terms of the sequence to be within 0.1 units of each other, then there is a position that you may locate. There is some position somewhere so that beyond that position, any two terms are within 0.1 of each other, as measured here. The distance between any two terms is less than epsilon. So roughly speaking, this statement, the definition of convergence, states that the terms of the sequence eventually get very close to L. And this Cauchy criterion effectively states the terms of the sequence eventually get very close to one another. And so certainly there is a relationship between these, and so you're probably thinking, what is the relationship between these? Are they the same? Are they related? Does one imply the other? Who knows? Well, if the terms get very, very close to L, then you would probably expect that as a side effect of getting close enough to L, then they become close to one another, right? I mean, if this number is close to L and this other number is close to L, then they can't be too far from one another. And so you might expect that if the sequence converges to L, then because the terms of the sequence are close to L, then they would likewise be close to one another, merely as a side effect of both of them being close to L. And if you suspected that, then you'd be right. What that means in this language is if a sequence converges to L, then it is Cauchy. What about the other way around? If the sequence terms get closer and closer to one another, does that mean that they're also getting closer and closer to L? Well, no, wait a minute. This is kind of a difficult thing to state, because if they're closer and closer to one another, we can say that by means of this Cauchy condition, but we don't even have a value L. So the real question is not, are they getting closer to L? The real question is, are they getting closer and closer to something, anything? Is there an L out there somewhere to which the sequence converges? And this is a very difficult question. It's far from obvious. If the terms get closer and closer to each other, is there some L to which they are converging? But the answer to this question is also yes. That if the terms are getting closer and closer to each other, then there will be some L that they are getting closer and closer to. But the proof of that is much deeper. So you might say, well, why would we even bother then, right? If we have a definition of convergence that works perfectly fine, and we've given all the limit laws in terms of this definition of convergence, and we've seen lots of uses for it, now it seems like we have a different definition of convergence, that the terms of the sequence get close to one another. It seems like this Cauchy criterion is a brand new definition of convergence, and if it turns out, as I just claimed, that this implies this and this implies this, then what's the point? It's just an equivalent definition. And so, okay, so on a certain level, it is just an equivalent definition, but the fact is, it's very, very hard to prove that a Cauchy sequence converges to some L. And that might seem like, okay, so let's not bother, right? But if we can prove that any Cauchy sequence must converge to some L, then there are a lot of sequences out there that we will not be directly, we can't directly show that they converge to anything, but we can directly show they're Cauchy. So what we're really doing here is we're trying to do this work once. For all those sequences out there that we don't know the L, but we do know that they're Cauchy, we're trying to show for all of them that they must converge to something, and we're trying to unite all of that work into an abstract theorem that says if a sequence is Cauchy, then it converges. So the real point here is, we'll prove that a convergent sequence is Cauchy. That will be pretty easy. We'll prove that a Cauchy sequence is convergent. That will be very hard, but it will be one-time work, and then we will have a lot of sequences that we can identify, oh, that's Cauchy, that's Cauchy, that's Cauchy, and we can immediately infer that they actually do have a limit and they do converge to some real number. So that's kind of what the agenda is here. So before we go on and try to do the harder part, let's try to do the easier half of this proof. If a sequence converges to L, then that sequence will be Cauchy. So this is not altogether hard, except that we have never discussed how to prove that a sequence is Cauchy. But that's okay, because you can infer how to prove that a sequence is Cauchy from this formula here, right? You have to start by saying let epsilon be greater than 0, and you have to continue by choosing a value of cap n, and then you have to let these be arbitrary, assume this, and demonstrate this somehow. So that must be what we're doing. So let's make that formal. So let's state this as a theorem. So if an converges to L, then an is Cauchy. And so the proof will begin by saying assume that the limit of an is equal to L. And so we have effectively assumed this entire statement by that statement. And then I wish to prove the Cauchy criterion for an. So the Cauchy criterion is this. And to prove something like this is universal in epsilon. So I'll begin by saying let epsilon be greater than 0. This is the same as the beginning of a proof that it converges to L, but we're not proving that it converges to L, of course. We're proving that it's Cauchy. It begins the same because logically these things begin the same. They're both universal statements about epsilon, followed by existential statements about n, followed by universal statements, but now we see a slight difference. So as usual, we don't really know how to choose the value of cap n, at least not yet. But we do know that that is our next obligation, right? Our next obligation is to choose the value of cap n, which will somehow make this true. Now, at this point, we have a placeholder for a choice of cap n, and then we need to continue to make a generalized claim about any m and n beyond that cap n. So let's let m and n be natural numbers, any two natural numbers. And now we have an implication, if this, then that, so we assume this part. So we assume here that m is greater than n, and n is greater than n, okay? And without yet knowing what choice we should be making for cap n, we don't really know what this entails or means to assume that m is greater than that value and little n is greater than that value. But we will, when we fill in the value of cap n, we will understand what we have said there. Now what? So now the agenda is to fill in this. We need to demonstrate that an minus am is less than epsilon. So, well, just as if we were proving an minus L were less than epsilon, if I were proving that, I would start like this, and I would do a whole bunch of computations, and I would attempt to end with less than epsilon. Here, I have a similar situation, but I have to begin with this. And now, now maybe we don't have any idea what to do. So let's think about what to do here. So this is the basic, this is everything we can say about the proof without really thinking about the mathematics, only thinking about the structure of the logical statement here and what it would mean to prove such a thing. So that's really as far as we can get without thinking really about the mathematics and the quantities involved. Now, we have this assumption here. And this assumption allows us to put an close to L. And it also allows us to put am close to L, although that's maybe less obvious. You see, this statement is universal in n. For any value, if it is greater than cap n, then an minus L will be less than epsilon. So this statement might empower us to say that AN was close to L, and it might empower us to say that AM was close to L. It might give us control over AN, and it might give us a corresponding control over AM, provided that we also knew that M was very far along the way. So the thing is, we would really rather compare AN to L and AM to L if we were interested in using this assumption, which we haven't yet used, that this limit of the sequence AN is actually equal to L. So if we're interested in comparing these to L, then the right thing to do is to add and subtract L to both sides, and that will basically allow us to compare these things to L. So let's go and compute, and this will be an equality, at least at first we'll have an equality here. So this might seem, again, a bit mysterious that we would just add and subtract this thing, but the motivation here is that I will have better luck comparing AN to L, and I will have better luck comparing AM to L than I will comparing them to each other, because the content of the assumption is this thing. And so I expect that to be a better comparison. Now here we have AN minus L, and here we have L minus AN. We're going to split this, of course, and when we split this, that's by the triangle inequality. So this gives us less than or equal to AN minus L plus L minus AM. Now, if you're looking at this and thinking, I can control that first thing, but I don't know what to do with the second one, well, that kind of makes sense, right? Because the first thing exactly matches what's here, and the second one is a little bit different. It's different in two ways. First of all, it's reversed compared to this, and second, it has an AM instead of an AN. And so let's ignore this one for a moment and see if we can control this one. How would we control this term? Well, what we could do in order to control this term is we could choose an n for epsilon according to the definition of the sequence converging here. And that would get this thing less than epsilon. But then the best thing we could hope for is an epsilon here, and that would give us 2 epsilon, which we don't really want. So let's try to control this so that it's less than epsilon over 2. Can we do that? Sure, because epsilon over 2 is also a positive number. And this is for any epsilon, there is a cap n. So what we can do is we can choose cap n for epsilon over 2 in the definition of this limit. And so that indicates what we might choose for n. Now, if I were nervous about this term and I didn't really know how to control this term, then I would say let cap n1, choose cap n1 for epsilon over 2 to control this thing. And then later I would anticipate choosing a cap n2, and then maybe cap n would be the max of them. And if I didn't already see what I was going to do with this, then that's how I would structure this proof. But I happen to see that the one cap n is going to be enough. So instead of having a cap n1 and a cap n2 and taking the max of them, I'm just going to choose cap n for epsilon over 2 in the definition of the limit, this thing. The limit of an is equal to L. And that is my choice of cap n for the purpose of proving that there is a cap n in the Cauchy definition. Now, that might seem a little reckless here because I've only controlled one term by that choice of cap n. But let's continue and see what happens. So what does it mean to choose cap n for epsilon over 2? It means that somehow I found a value of cap n such that for every n which exceeds cap n, then this term is less than now epsilon over 2. And so that means that I can certainly write here, this is less than epsilon over 2 plus, but now I have this ugly term that I still haven't sorted out. And do I really know that little n is beyond cap n? Yes, because I have assumed it here, right? So because of the structure of this proof, let m and n be in the naturals and assume that they are both greater than cap n. So I have assumed that n is beyond this value cap n, and so I really do know that an minus L absolute is less than epsilon over 2. Now what to do with this term? Well, first thing I might worry about is that it seems backwards from what I've got control over here. But that's actually not a problem at all because it's in absolute value signs. If you want to reverse its order, then go ahead because it's within an absolute value sign. If you reverse this thing and turn it around backwards, you just negate it. But you're negating it inside an absolute value right before taking its absolute value. So negating a term right before taking its absolute value doesn't make any difference, and you can feel free to reverse it. The next thing we would worry about here is that am is not an, and it seems we only have control over an. But notice here that the assumption that we've got here, that an converges to n, that it converges to L, is an assumption which is telling us there is a cap n, which we've used, such that for any value in the naturals, if that value is greater than cap n, then that value minus L, absolute is less than epsilon over 2, because we applied epsilon over 2. That's true for any value that exceeds cap n. It doesn't matter if we call that value little n, or little m, or little l, or something else entirely, so long as we have an integer which is greater than cap n, well, a natural number, which is greater than cap n, then when we put it here, we will get an absolute value less than epsilon over 2, because that's the value we applied it to. And so, is little m greater than cap n? Sure, because we assumed it right here. So everything that we've said about little n actually applies equally to little m just as well. And so this thing is also bounded by the same epsilon over 2. And I could have done this in fewer steps, but I wanted to showcase how we sort of sort this out, and then this kind of happens as a side effect. And that gives us, of course, epsilon. So basically, the long and the short of what's happened is that by forcing every sequence term to be less than epsilon over 2 from L, any two sequence terms can be at most a distance of epsilon apart, right? This one could be less by almost epsilon over 2. This one could be more than L by almost epsilon over 2. And then the distance between them would be almost epsilon, but it could not exceed epsilon if they were both that close to L. So that's kind of what happened here. And this is our proof of that. So this establishes that if a sequence converges, then it is a Cauchy sequence. Now, what we need to do next is we need to show that if a sequence is Cauchy, then it converges. This is much, much harder, because in order to show that a sequence converges, we have to say to what. And if we know that a sequence is Cauchy, we don't even have an L around to refer to. And so this is much more challenging. The proof needs to run in stages. And so let's talk about the various pieces of the proof. The first part is that if we have a Cauchy sequence, then it is at least bounded. So let's state the theorem, and then I'll talk about the structure of the proof. So if an is Cauchy, then an converges to some L, right? There must be some L out there somewhere to which it converges. And so the structure of the proof here, I'm just gonna give the bird's eye view of the proof without details, and then we'll start getting into the details here. So the structure of the proof is like this. The first thing we're gonna show is if an is Cauchy, then an is bounded. And that's actually fairly easy to prove. So if it's a Cauchy, then it's at least bounded. Now, bounded doesn't mean that it converges. So that's really a very weak condition. And then we're going to show that if an is Cauchy, so if an is Cauchy, we're going to show it has a bounded monotone subsequence. Oh boy. A bounded monotone subsequence. Now we have not defined subsequence, but what I want you to think about is some of the terms, but not all of the terms, right? You've got an infinite list of terms. Just pick out some of them, like the even ones, for example, or just the odd ones, or just the ones whose index is prime, or something like that. Just pick out some of the terms, but not all of the terms. If you pick out some of the terms, but not all of the terms, then that will be, if the original sequence is bounded and you pick out some of the terms, that will be bounded, and then it will be a monotone subsequence. And then we're going to show, so why do we want a bounded monotone subsequence? Because we have the bounded monotone convergence theorem that says if you have any sequence at all and it's bounded and monotone, then it will converge. But that doesn't even prove that an converges, right? it proves only that a subsequence of AN converges. And so what we need to do finally is to show that if AN is Cauchy and has a convergent subsequence, then AN converges. And that's to the same limit as the subsequence. So this is how the puzzle pieces are going to go together, but we haven't proven any of these pieces of the puzzle yet. So we need to have 3 independent results here. The first result will show us that this Cauchy sequence must be bounded. The second result will say not only is it bounded, but it has a subsequence which is likewise bounded and also monotone. Then that subsequence will converge, but then we need to say, okay, if the subsequence converges, then the original sequence converges as well. And so that's how we're going to structure this proof that a Cauchy sequence AN converges to some L. So we're going to prove this in 3 stages here. Now, let's get started on this first statement. If we have a Cauchy sequence, then it's bounded. This is actually pretty easy. So let's take an arbitrary Cauchy sequence. So proof of 1. So let AN be Cauchy. Now we need to show that it's bounded. Well, we have no tools available except well, the definition of Cauchy. So let's let epsilon be 1. Oops. Let epsilon be 1 and choose n for epsilon in the definition of Cauchy. Okay, so that's really the only tool available to us. We have that this sequence is Cauchy, so that's all we can do is choose some way to use the definition of Cauchy. And so I've just picked an arbitrary epsilon here, and I've chosen n in the definition of Cauchy. Now I'm going to say, well, what do we know about that n? We know that for any m and n beyond that, then this distance is less than epsilon. Okay, so what I'm going to do next is I'm going to pick a certain little m. Okay, so next I'm going to choose a little m greater than n. Well, I should point out that I'm choosing it in the naturals, right? Choose a little m in the naturals with m greater than n. And then what do we know? We know then for all n in the naturals, if n is likewise greater than n, then we know that the absolute value of an minus am is less than epsilon. So we have these sequence terms, and we read far enough down the sequence that all the terms after that are within a distance of 1 from each other. And this epsilon is going to be 1 here. So then we pick one that is within that set and beyond cap n. And then we know that every term beyond cap n is going to be within a distance of 1 from that particular term, am. All right, so what? Well, that gives us something about an. That tells us that an is going to be sandwiched between am plus 1 and am minus 1, right? So these are bounds for an. And I would love to say that therefore the sequence is bounded. It's bounded by the upper bound am plus 1 and the lower bound am minus 1. And it kind of looks like we're ready to conclude that the sequence is bounded. But that statement is only true for the values of little n which exceed this cap n, which could be like 1,000,000, for example, right? If cap n is 1,000,000, then what happens is we have 1,000,000 terms of the sequence, and then we have this kind of control where we can say we have this upper bound and we have this lower bound. But the first 1,000,000 terms of the sequence, they could be doing anything, right? And so they don't have to obey these upper bounds. So, oops, we controlled all except some unknown number of terms, and that number is basically cap n here. What are we going to do about that? Well, there are only finitely many terms that are not under our control here, right? We have control of the infinitely many terms starting at cap n and onward. We do not have control of the finitely many terms from little n equals 1 to little n equals cap n or round it down, whatever. So there are finitely many terms at the head of the sequence that we don't have control over. But those finitely many terms, they have to have a max, right? So, and they have to have a min. So what we're going to do is we're going to let little m be the min of all the ANs for n less than or equal to cap n. We're going to take the min of that set. Let me put this in set braces. But we're also going to take within that min am minus 1 itself. Sorry, not a sub n minus 1, but am minus 1. So this single element, which bounds the infinitely many in the tail of the sequence, plus all of these elements, which are, we're taking the min of them all, and then that's going to be a lower bound for the sequence. And similarly, we're going to take all of those elements, all of those early elements, together with the bound for the rest, and we're going to take the max of all of those. And then no term of the sequence can exceed this maximum, and no term of the sequence can be less than this minimum. So then we can safely say for all n in the naturals, so m is less than or equal to an is less than or equal to m. But let me say why, just in case it's not obvious. These two bounds themselves will make this statement true if an is in the tail of the sequence, if n exceeds cap n. But this is a min of a whole bunch of values here, right? If n is less than or equal to cap n, then it will appear in this list. And so the minimum of this entire list will be less than or equal to an. And so an will have to be greater than or equal to the min in a list of things that includes it itself. And so this thing will be greater than or equal to cap n. And similarly, if little n is less than or equal to cap n, then an will be in this list as well. And so it will have to be less than or equal to a maximum. Sorry, that's supposed to be a max. It will have to be less than or equal to a maximum of things that includes it itself. And so we get that. Now, if an is in the tail, then, well, it will be less than or it will be strictly less than an plus 1, and this maximum must work out to be at least that, because that value itself is in the max. And so one way or another, an will be less than or equal to cap n and greater than or equal to little m. And so an is bounded. So an is a bounded sequence. In principle here, what we're really doing is we're showing that it's eventually bounded. And then we're showing you don't really have to worry about the head of the sequence, right? The tail of the sequence is an infinite set. That's what we really should be worrying about if we're worried about bounded. The head of the sequence is a finite set, and every finite set is bounded trivially by just take the max of those finitely many numbers. So basically what we're doing here is we're saying, let's figure out the tail of the sequence and prove that it's bounded, which is the really significant part, and then the head of the sequence is bounded just because it's finite. So that's a proof of 1, and that helps us understand that if an is Cauchy, then it is a bounded sequence. So the next thing we need to do is we need to say that if an is Cauchy, it has a bounded monotone subsequence. Now, the way I phrased this, it makes it look like it's about Cauchiness. But actually what we're going to do is this is not even a statement about Cauchy, not yet. What we're really going to prove is that every sequence has a monotone subsequence. Whether it's Cauchy or not, whether it's convergence or not, whether it's bounded or not, every sequence has some monotone subsequence. And then if the sequence is Cauchy, then it's bounded, right? So that will give us the rest of this. So what we're actually going to prove here for 2 is just that every sequence has a monotone subsequence. And this is a really interesting and kind of a peculiar proof that I've always had a sort of an affection for. So let's, I'm going to erase these definitions, and then we're going to prove that every sequence has a monotone subsequence. But I haven't defined a subsequence yet, so let's talk about subsequences. So the first thing I want to do is I want to talk by example about subsequences, because having the examples in your head will make it a lot easier to understand what this is really about. So let's talk about examples, and then I'll give a rigorous definition. So examples of subsequences. So if AN is the sequence 1 over 1, 1 over 4, 1 over 9, 1 over 16, 1 over 25, 1 over 36, etc., then a subsequence might be a sequence like 1 over 4, 1 over 16, 1 over 36, 1 over 64. I'm just picking out the even, the reciprocals of the even squares there instead of all of them. So if AN is going to be a sequence like 2, 4, 6, 8, 10, 12, 14, 16, then a subsequence might be a sequence like 4, 6, 10, 14, and maybe it's not obvious what I'm doing here, 22, 26. These are all the even numbers, and these are just some of the even numbers. And maybe it's a completely arbitrary list of some of the even numbers, or maybe you'll notice that these are double the primes. So I picked out the prime indices. Well, I picked out the prime indices. No, not exactly. I've picked out the ones that are double the primes, and the subsequence is those. So if AN is going to be something like 1 plus 2n over 1 minus 2n, then we might get a sequence, well, let's make this a little bit simpler. If AN was going to be a sequence like 1 plus 1 over n, then that would give us something like 2, and then 1 and a half, and then 1 and a third, and then 1 and a quarter, and then 1 and a fifth, and then 1 and 1/6, and etc. And then a subsequence might be something like 1 and a half, and 1 and 1/5, and then 1 and 1/8, and then 1 and 1/11, and then 1 and 1/14. It's just some of those terms, and I'm increasing it by 3 each time, but it doesn't even matter. Just any of these terms in the same order. Now, a subsequence cannot reorder the terms, right? I couldn't start with this one and then move on to 2. We have to take the terms in the right order, but basically we're knocking out some of the terms and keeping some others. Now, it's very difficult to give a formula for the subsequence given the formula for this, right? Because the subsequence might be rather complex. It's also very difficult to give the right notation for the subsequence, and that's what we need to talk about next. So the fact is, when we have a subsequence, what we have done is we've picked out some of the terms of the sequence. But what we have really done is we've identified not the terms to keep, but the positions to keep. So instead of thinking, I'm going to keep a quarter, I'm going to keep 1/16, you should think, I'm going to keep the second position, and I'm going to keep the fourth position, and I'm going to keep the sixth position. So don't think of a subsequence as keeping some terms and excluding other terms. The reason you shouldn't think of it this way is because many sequences can have like a lot of repeated terms, right? So you wouldn't want to just say, I'm going to keep the 1, right? Because which one? So you could have a subsequence of this, which is like quite surprising, like -1, -1, 1, -1, -1, 1, -1, -1. If you play your cards right, you can make this thing a subsequence of the original alternating sequence. How would you do it? Well, you would take this one, and this one, and this one, and then this one, and this one, and this one. And then you would get the sequence to go 1, -1, -1, 1, -1, -1. So don't think of it as picking out the individual terms. Think of it as picking out the locations. Now, the locations themselves have indices. This is index 1, this is index 2, this is index 4, and 5, and 6, and 8. Up here, this is index 2, and index 4, and index 6. And when we say that that's index 6, what I mean is a sub 6 is equal to 1 over 36. And when I say that this is index 8, I mean that a sub 8 is minus 1. So in order to identify a subsequence, what we really need to communicate is which indices are used. And in order to communicate which indices are used, we need to have another sequence, the sequence of the indices that are used. Okay? So here, I want you to think of the sequence 1, 2, 4, 5, 6, 8, etc. as a sequence, and it's a sequence which describes which indices to keep. Here, I want you to think of the sequence 2, 4, 6 as a sequence, and it describes which indices to keep. So really, there's a kind of a meta-sequence, but it's really just a composition of functions that we're dealing with. So let me explain how we think about this and how we use notation to describe this. So let's pick this example because it's probably the simplest. So what I'm going to do is I'm going to make a table of values here for this sequence. So if the n values are, actually, let me make a table of values vertically, and let's erase this because we don't need it. So in this example, we can make a table of values in a straightforward way. We can make the values of n and the values of an. When n is 1, an is 1 over 1. When n is 2, we get 1 over 4. When n is 3, we get 1 over 9. When n is 4, we get 1 over 16, etc. So this is a simple way to make a table of values, etc. But now I want to describe the table which gives us the indices of interest. And so I'm not going to make that a function of n. I'm going to make that a function of k. When k is 1 or 2 or 3 or 4, then we're picking off an index of interest. And the index that we're picking is the 2 or 4 or 6 or 8 indices, these guys, right? So the first index to pick is index number 2, right? That's why I say that the first is 2. And the second index to pick is index number 4. 2 goes to 4. And the third index to pick is index number 3. It is index number 6, and so the third goes 6. Now, these numbers are still indices of the sequence an. So they really are values of n. And what we typically do is we write this n. But it's not good enough to just write n, because that n is a function of k and depends upon k, right? And so to communicate that that n, that position within the sequence an, is actually dependent on k, we write this n sub k, okay? So when k is 1, n sub 1 is like the first index you want from the subsequence, and that's equal to 2. When k is 2, n sub 2 is the second desired position for the subsequence, which is position 4. So n sub 2 is 4. But this is not the sequence of interest. This is not a subsequence at all of the original sequence. What we want is the original sequence as we apply it to just those positions. And so what we have to take is we have to eventually apply the rule for the sequence. Now, when we do that, what we're doing is we're taking one of the sequence terms. So this is a sub n, the sequence term, that depends on n. But it depends on n, and we've called the n sub k to communicate its dependence on k. And so this is a sub n sub k. This may look very, very complicated, but on a certain level, it is nothing more than composition of functions, right? You take the k, which describes the numbering within the subsequence. A function of that is n sub k, which is the numbering within the original sequence. And then, having the n sub k, then what we do is we take that term of the sequence. So let's do another one here. Let's examine how this will work for this subsequence, which is the doubles of all of the prime numbers here. So in that sequence, what we would have, so if we just look carefully at this example, we want to pick off 4, 6, 10, 14, and 22. So from the sequence whose original terms are simply the evens. So we want this one, and we want this one, and we want this one, and we want that one, and then we want to pause for a while until we get to 22. So 18, 20, 22, 24, 26, 28. So we'll take this one, please, and this one, please. All right, so the first thing to identify is what are the actual positions taken. This is position 2, and this is position 3, like 1, 2, 3, right? So the first position taken is n sub 1, and that's 2. And then position 3 is taken, and then position 5. Now, these are the first and second and third terms of the subsequence that we're generating. So notice, the subsequence is indexed by k, but k is telling the locations of the original indices within the original sequence. So the first term of the subsequence is the second term of the original sequence, and the second term of the subsequence is the third term of the original, and the third term of the subsequence is term 5 in the original, and that's what I'm noting here. So this will always just be numbered with 1, 2, 3, 4, 5, 6, 7, and then this will tell us the locations within the original sequence that we want to pick. This is position 5, 6, 7, 8, 9, 10, 11, 12, 13, and of course the next one will be 17 because I was making the prime numbers. Now when we so this is not yet the subsequence. This is just the indices where the subsequence lives within the original sequence. If we want the subsequence, we have to actually grab the n sub k terms, and those will be 4 and 6 and 10 and 14 and 22 and 26 and 34, because this is just the doubling rule. So this a sub n sub k business is very, very confusing. K is the position within the numbering of the subsequence. N sub k is the position within the numbering of the original sequence. And a sub n sub k is that term, that particular term. So with all of this in mind, now we can give a simple definition of a subsequence that basically sums all this up. So the only thing I haven't actually mentioned explicitly is we have to pick off the sequence terms in order, and that means not picking one of them again and again and again and again and again, right? So if n sub 3 is 5, n sub 4 cannot be 5, and it can't be 4. It has to be greater than 5. And so n sub k as a function of k has to be an increasing function of k, strictly increasing function of k. All right, so I think I have room here to write a formal definition of a subsequence. So definition. So let n in the naturals be a sequence. So a subsequence is a sequence indexed by k a sub n sub k, where k is in the naturals, and here where n sub k is also a natural and n sub k is a strictly increasing function of k. In a way, it's just a sequence composed with a strictly increasing function from n to n. But the notation makes this really rather difficult. The reason we use this notation is we want the n sub k to correspond to the n, right? If you have an n, which is the subscript of the original sequence a sub n, then we want something like an n. to be the subscript on that A. And so we choose A sub n sub k, which is ultimately a sequence that depends upon k now, not on n. And k is the counter that walks through these things that I've noted in blue, whereas n is the counter that walks through these things that I've noted in black. So that's what a subsequence is. That was complicated. So that's a formal definition of a subsequence. Now, I have a claim here that I claimed that I would prove for you, and that is that every sequence has a monotone subsequence. In other words, if you have any sequence, then there must be some way to pick out some subsequence of infinitely many terms so that they are either all increasing or all decreasing. And this is a really sneaky and interesting proof. So let's erase these examples, and we'll prove that every sequence has a monotone subsequence. All right. So let's state this carefully. It's a very short statement. Let AN be a sequence of real numbers then AN has a convergent subsequence. No, sorry, a monotone subsequence. There are a lot of different ways to prove this, and my favorite way is not an appropriate choice for this course. This statement is related to Ramsey theory, and it can be proved with ultrafilters, and there are lots of beautiful approaches to this. But in this course, the main agenda is to keep it simple when possible. And so we're going to give the simplest proof I know of this, and it starts with a basic idea. The basic idea is even if the sequence oscillates up and down and up and down, let's graph the sequence. So let's imagine we have a sequence here. We're going to think very geometrically here. So this is going to be n, and then this is basically going to be a graph of the sequence. So if the sequence, like, maybe it goes down like this and converges to 0. Maybe it goes up and down and up and down. We're not assuming that the sequence converges. So this graph could look completely arbitrary. But so let's imagine that we graph the sequence and it goes up and down and up and down. And because it goes up and down and up and down so frequently, notice I'm only putting dots, not a connecting line, because we only have values of a sequence at the natural numbers, right? So this would just be a sequence of dots here if you wanted to plot it, and you would have a dot for every natural number. Now, I'm trying to make this look very complicated because I'm trying to give you the suggestion that it might not be obvious how to find a monotone subsequence of this. It's not even obvious whether we should look for an increasing sequence or whether we should look for a decreasing sequence. And that's part of the real complexity of this, because every sequence has a monotone subsequence, but not every sequence has a decreasing subsequence, right? Some of them just keep going up. Not every sequence has an increasing subsequence. So we don't even really know which of these two we're looking for, but it's hard to look if we don't know yet. So I want to sort of indicate, let's move this point upwards a little bit so that we can have something to go on here. There is a kind of an interesting kind of sequence term which is useful in this proof for finding the monotone subsequence. And the terms that are interesting for this purpose are the terms that are not the very max value of the sequence, but higher than all of the subsequent values. So here, this is kind of what I'm talking about here. And let me highlight this point in red. And then if the picture is to be believed, what is important about this red point? So that point, let me downgrade some of these to make it more geometrically obvious that it's the case. So that point is the highest point in the sequence, right? If we assume that everything we see here is represented, that point is the highest point in the sequence. It's higher than everything that came before, and it's higher than everything that comes after. This point is also interesting. Now, it's not the highest point in the sequence, but if the picture is to be believed, then it is higher than everything that comes after. And this point here is also higher. It's not the maximum value, it's smaller than this value, but it is, if the picture is to be believed, higher than everything that comes later. And these points are interesting, and they're the ones that are going to help us prove this. So what we need to do is we need to identify them by name, and I'm simply going to call them high, okay? Because they're higher than everything that comes later, but they're not necessarily higher than everything that comes before. So actually, I've heard them also called a summit, which I think is an interesting term for them. So let's use that term. So let's call this kind of point a summit. So let's officially declare the beginning of this proof. We're going to prove this, and let's officially declare the assumption. Let AN be a sequence. Okay. Now, we call a term A sub n, and I'll put this in red because it represents the red points here, a summit if A sub n is greater than or equal to A sub m for all m beyond n. So that's really what I'm saying when I say it's higher than everything that comes later, right? Every m greater than n, then it's going to be less than or equal to that value. So in this picture, I've got 3 summits, and arguably I could identify a few more summits here, right? If the picture is to be believed. But honestly, like if the next point in this picture is here, then none of these things were summits, right? So the picture is supposed to be suggestive of what's going on, but you have to imagine that it keeps kind of staying within this range down here. So a summit of a sequence is a term it's not greater than every term of the sequence, but it's greater than or equal to all of the future terms of the sequence. Now, what we're going to do is we're just going to tie together the summits and make a subsequence out of them. Now, there is a little bit of a sticky point that we should be concerned about, whether that's actually possible. So, but let's ignore that for the moment. So if there are infinitely many summits, then each is less than or equal to the previous. In other words, they go down, right? I mean, because each one, if it is a summit, then, you know, it's greater than or equal to everything that comes later. And so each summit is going to be a little bit smaller, well, less than or equal to the previous summit. And if so, then they form an infinite descending subsequence. So the summits of the sequence form an infinite descending subsequence. Now, if you believe this proof so far, if you already believe this proof, then what I've actually proven is that every sequence has a decreasing subsequence. And that can't possibly be true because, you know, curve going straight up is not going to have a decreasing subsequence. So there must be something missing from this argument. And so what is it? I mean, let's go through it again. We define a summit to be something greater than or equal to all of the future terms. If there are infinitely many summits, then you just pick them and they themselves form a decreasing subsequence. Maybe not strictly decreasing, but weakly decreasing. Each one is going to be greater than or equal to the next, and then it'll go down or stay equal each time. Well, what's missing is, well, what if there aren't infinitely many summits, right? So, I mean, it's possible that there are only finitely many summits. Maybe there are 100 summits, and then you run out, and then there aren't any more summits. So let's assume, so this is a different case, and so basically, what if not, right? If there are infinitely many summits, then we win. What if not? So if there are finitely many summits, then they stop. There's a last summit. And let's call that last summit A sub cap n. The very last summit. And then that is a summit. It is greater than or equal to every future term. Maybe there are no summits at all. In fact, then skip this point and don't worry about it. We don't really need the last summit. What we need is to make sure that we are beyond all of the summits. Okay, so if there are no summits, then that's okay too. So choose a term. So A sub n sub 1, our very first term in the subsequence, beyond all summits, if they exist at all. So maybe this is the very last summit. Then this one can be A sub n sub 1, right? Maybe there are no more summits, and then this one can go. And if there were no summits at all in the first place, then anything will do. So we're going to choose a term beyond all the summits. Is it a summit? Of course not. What does that mean? That means it is not greater than or equal to everything that comes next. It might be greater than or equal to lots of things that come later, but it's not greater than or equal to everything that comes later. So there must be something later in the sequence which is greater than it, right? That's going to be A sub n sub 2. So choose A sub n sub 2 beyond A sub n sub 1 so that A sub n sub 2 is strictly greater than A sub n sub 1. And then maybe you see where we're going. A sub n sub 1 is not a summit. That means there's something further down that's even bigger. But that is not a summit because we're beyond all the summits anyway. That can't be a summit either. That means that there's something farther down from that where the term of the sequence is even larger. And so we can continue going in this way. We can choose an A sub n sub 3 beyond A sub n sub 2 so that A sub n sub 3 is greater than A sub n sub 2. And then we have just one more line, but we only have one more thing to say. That means that, so if we just continue in this way, so what do we get? So continuing, so A sub n sub 1, A sub n sub 2, A sub n sub 3, A sub n sub 4, etc. is an increasing subsequence. So that proves that one way or another, there will be a monotone subsequence. If there are infinitely many summits, the summits themselves will form a monotone decreasing subsequence. If there are finitely many summits, then you read beyond them all. If there are none, you just start wherever, it doesn't matter. You read beyond them all or start anywhere, and then each term, because it is not a summit, can be exceeded by something later, which can be exceeded by something later, which can be exceeded by something later, because there are no more summits. And so then we get a monotone increasing subsequence. So if the summit trick works, we get a monotone decreasing subsequence. If it doesn't work by virtue of its failure, we will get a monotone increasing subsequence. And so one way or another, the original sequence has some kind of monotone subsequence. And that demonstrates that every sequence has a monotone subsequence. Now, does that handle 2? Well, yeah, basically it does. We have demonstrated that if a sequence is Cauchy, then it's bounded. So if we have a Cauchy sequence, every sequence has a monotone subsequence. That Cauchy sequence will be bounded and will have a monotone subsequence. And that monotone subsequence will itself be bounded. And so that handles 2. We have only one more step in this very long proof, and that is if AN is Cauchy and has a convergent subsequence, then the original sequence likewise converges. So this is maybe not as easy as it sounds. A subsequence can converge even if the original sequence doesn't converge. And you can see that most clearly in the alternating sequence, 1 minus 1, 1 minus 1, 1 minus 1. That thing has subsequences that are just constant. And so of course they're convergent, but the original sequence doesn't converge. But in part 3 here, what we're claiming is if it has a convergent subsequence and is Cauchy, then it will converge. Now, so let's prove that, and then we'll tie it all together. So we're going to take a Cauchy sequence, which is for some reason known to have a convergent subsequence. So this is our next theorem. So let AN be Cauchy with a convergent subsequence A sub n sub k. Then the conclusion of the theorem is then so actually, if it converges, it will be convenient to say the limit of A sub n sub k is equal to something in particular, and we'll say L. And notice that A sub n sub k is truly indexed by k. And so this is really the limit as k goes to infinity of A sub n sub k. Then the conclusion here is that the limit of the original Cauchy sequence, A sub n, is also equal to L. And it's not too hard to prove. So this won't be much longer. Let's see what happens next. So I'm going to assume all the hypotheses. We have a Cauchy sequence, a convergent subsequence, and the limit is L. So I need to show that the limit of the Cauchy sequence is likewise equal to L. How are we going to do this? Well, same way we always prove limit questions. We're going to let epsilon be greater than 0, and we're going to choose cap n by some magic. So actually, what I'm going to do is I'm going to choose cap n to be, I'm going to have to choose cap n rather carefully here. Let's see, I need this thing to be close to L, and I need them also to be close to each other. So in what order should I do this? I should probably get this thing close to L first. So let's choose. So I'm going to choose a cap n, let's say 1, for epsilon over 2 in the definition of the limit as k goes to infinity of A sub n sub k equals L. So that if k is greater than n1, then A sub n sub k minus L absolute is going to be less than epsilon over 2. And notice here, this thing is indexed by k. So we have if k is greater than this thing. That should be supposed to be like a lowercase k is what I mean here. So in other words, I'm leveraging the fact that this thing approaches L. Now next, I can't get these things directly close to L, but I can get them close to these things by using the Cauchy criterion. And so let's use the Cauchy criterion to get all of these terms close to each other. So choose an n sub 2 for epsilon over 2 in the definition of Cauchy for A sub n. And that is if m and n are both greater than n sub 2, then an minus am absolute is going to be less than epsilon. So we've got the terms of the subsequence eventually close to L, and then we've got these things close to each other. Now, I want both of these things to be simultaneously true, and so I'm going to pick the max. I'm going to choose cap n to be the max of n1 and n2. Now, then I'm going to choose, what am I going to do here? What am I trying to do? I'm trying to establish that the limit of an is equal to L. And so I've chosen an epsilon, and I've chosen an n, which I hope will work. Hopefully, keep your fingers crossed. This n will work. And then what do I need to do? I need to choose an n beyond, and I need to establish the difference between an and L is small. So let's choose an n in the naturals and assume that it's greater than cap n, and everything should be fine. So let's say, okay, let's measure the difference between an and L. So an minus L, this distance is going to be less than, now I'm going to insert a term a sub n sub k. And which one? Well, it really doesn't even matter which one, so long as it's big enough. So this is going to be less than, well, that's going to be equal to this thing, and then we're going to get a sub n sub k, and then minus L, and we're going to split this by the triangle inequality. What I'm trying to do is I'm trying to compare the terms of the original sequence to some term in the subsequence. Now, will this work? Well, I want control over this. And so when I insert a sub n sub k, I need to make sure that I insert a value here which satisfies this condition. So basically, I'm going to choose a particular k which is greater than n1 here. So here, choose a k greater than n1. And notice that n sub k is also greater than n1. Why does this matter? It matters because, actually I'm going to choose k greater than n here. And then n sub k will also be greater than n because it's an increasing sequence there. Why do I want n sub k greater than 1? Because I want this condition to be true. So actually I want both of these conditions to be true. So once k is greater than n, it will be greater than n1, and then this condition will be true. But I will also have n sub k greater than n, and I will have a confidence that this condition will also be true. So I'm going to choose k greater than n, and any choice will do here. At this point, when I choose k greater than n, anything will do. Then I'll get this thing. So let's look very, very carefully at the conditions and see whether they're met here. K is greater than n. N is the max of these two values. That means k is greater than n1. If it is, then this thing will be less than epsilon over 2. And so that thing is this thing, and so this thing will be less than epsilon over 2. Do I actually get control over this? Well, let's see. N sub k itself is greater than n, because k is greater than n, and n sub k has to be an increasing sequence, so this thing will also be greater than n. So if n sub k is greater than n, then it is like adequate for being m here, right? It's greater than n, that means it's greater than n2. That means it's like one of the m's that we are allowed to compare to. It is a value greater than n2. And so this thing for n sub k and for m really does apply, and it tells us that this difference, a sub n minus a sub n k, is indeed less than epsilon over 2. And I wrote this wrong, but I want to correct it here. Choose n sub 2 for epsilon over 2 so that this is less than epsilon over 2. So the point here is that n sub k is greater than n. It is like one of these m's about which we know that this thing will be less than epsilon over 2 because we've chosen it that way. And so this thing will be also less than epsilon over 2, and that will give us the epsilon that we need. So verifying that this really is proving the right thing, we have, let epsilon be arbitrary. Eventually, there is a choice of n. We have an arbitrary little n chosen greater than n. And then we have a supplemental choice here, but whatever. I mean, there is some little k greater than cap n, and if we need that little k greater than cap n in order to make this work, then we may use it, right? So we have this extra choice here, but that's okay. That was used to get this approximation working. And then we have an minus L is equal to epsilon. And this demonstrates that the original sequence an converges to L. So an minus L less than epsilon is the right conclusion for that limiting statement. So this demonstrates that if an is a Cauchy sequence with a convergent subsequence, then basically it gets dragged along for the ride, right? The terms get closer and closer to each other. They also get closer and closer to the terms of this convergent subsequence, which converges to L, and the original sequence, the original Cauchy sequence has no choice but to also converge to L. It gets, I think of it as it gets dragged along for the ride along with this subsequence which is converging to L. Okay, so that establishes part 3. And now, as I hinted at the beginning, these 3 together tell us that a Cauchy sequence converges. Let's just go over that one more time to make sure that it's clear. So if we have a Cauchy sequence, then it must be bounded. And because it's a sequence at all, it has to have some sort of monotone subsequence. So that'll give us a monotone bounded subsequence. Oh, we have theorems about monotone bounded sequences. The monotone bounded subsequence that resides within the Cauchy sequence, that converges. But that means that we have a Cauchy sequence with a convergent subsequence, and then this theorem applies and tells us that the original Cauchy sequence, all of it, that converges as well to some limit L. And that is a proof of the Cauchy criterion for convergence. If a sequence is Cauchy, then it converges to some value. Now, back to the beginning and what it all means. That was an awful lot of work to show an equivalence, to show that a Cauchy sequence, the Cauchy if and only if convergence, right? So what did we learn from it all? We introduced a new definition and then proved that it's equal to an old definition. Like, what was the point? The point was there are a lot of sequences that really, really are very hard to show they converge to anything at all. Like, even if you, I don't know, converge, diverge, it's really, really hard. And even if they do converge, it's extremely, extremely hard to identify that limit L to which they converge. And for these sequences, often the right and best thing to do is to not try to figure out what the L is, because you just can't. It's not practical. Instead, for these sequences, what we do is we just show that the darn thing is Cauchy. Once we know that the sequence is Cauchy, then we can invoke this theorem. And because this is a theorem, we only have to do the work once. We don't have to repeat all of this logic. We just say, hey, my sequence is Cauchy. It must converge to something. So let's just call that thing L. Now, if you actually want to know what it is, then you have to do some computation. But if your real interest is to show that it must converge to something, then this criterion will come in and save the day. So for all of those sequences for which we think it converges, but we just don't know to what, then this is really the right solution to allow us to prove, hey, it's Cauchy and therefore it must converge to something.